Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome again with your instructor Dr. Mohit Agrawal. We are going to start with lecture 2 of module 5. In the lecture 1, we learnt about the case of the flat earth layers. In today's lecture, we are going to have a detailed view of the dipping interfaces, and we will also learn the application of refraction seismology in the crustal structure. So the concept that we are going to cover today are, before we move on to today's lecture, we will have a recap of what we learnt in the previous lecture, and then we will be learning about refracted waves for the dipping layer case, and then we will see its application to identify the features in the crust that will be inferred from the refraction seismology. And then at the end of today's lecture, we will be having the summary of whatever we are going to learn today. So as far as the recap is concerned, we learnt about the application of seismology in the determination of the distribution of the seismic velocity or the elastic properties, and also the densities variations within the earth. If you want to find out the seismic velocity variations and hence the variations of the elastic properties, you will have to take help of the two techniques in seismology. One is reflection seismology, another is refraction seismology. So the refraction seismology and reflection seismology both take advantages of the travel times of various seismological phases that arise in a seismogram, and those arrival times can be used to find out the location of the source, and also can be used to find out the properties of the medium to identify the various interfaces in the depth, as well as the velocity of the layer and also the velocity of the underlying half space. So for that purpose, the travel time as a function of the offset we can calculate for three kind of phases. One is the direct phase, another is the reflected phase, and the third one is the head wave. As far as the direct wave is concerned, we can calculate the travel time for the direct phase as the offset distance divided by the top layer velocity that is given here. Likewise, we can calculate the travel time for the reflected wave, that is a hyperbolic curve in travel time with respect to the offset. So the equation of the reflected wave travel time goes like this: x square by v naught square plus 4 h naught square by v naught square. Similarly, for the head wave, the equation is x by v1. v1 is the velocity of the half space, plus 2h naught. H naught is the thickness of the layer, in bracket 1 by v naught square minus 1 by v1 square to the power under root. If we write this expression in the concise form, then it can be x by v1 plus tau, where tau is the intercept time and x is the offset, v1 is the velocity of the half space. If you look at these equations very carefully, then the top equation represents the equation of the straight line, the second equation is the equation of the hyperbola, and the third equation is again the equation of the straight line. So in the previous lecture we learned that if we make the travel time curve of all these three phases, then the time will be on the y-axis and offset distance will be on the x-axis. Then we can see the straight line for the direct phase will be here, and then you have the reflected wave that will be your hyperbola, and this reflected wave hyperbola will be asymptotically touching the direct phase, and then we'll be having the head wave which will be somewhere here, and that will be the shallower than the direct wave, because the velocity of the head wave in the layer will be the higher amount of velocity than the velocity in the top layer for the direct wave. So, and this, if you extend this head wave onto the y-axis, then wherever it will intersect, it will represent your intercept time, that is tau or tau1. Likewise, what we learnt in the previous class is the thickness of the successive layers can be found by starting with the top layer. That is what it means, is that if you have n number of layers, if top layer is n is equal to 0, n is equal to 1, and then likewise you have n is equal to n minus 1, total number of n layers are there, then the successive thickness you can calculate by using equation 1 and 2 of the previous lecture, that was for the intercept time and for the crossover distances, and then incorporate those values of h into these equations to find out the various other parameters. Now let's look at what we can learn in today's lecture. So in the previous lecture we started with the refraction seismology for the flat layer earth case, and where the layers were completely flat. Now we can extend those ideas for the case of dipping layer interfaces. So the refraction method can also be applied if the interfaces between layers are not horizontal. Conducting, for this purpose, what we are going to do, if suppose there you have a surface and there is a dipping interface, and for this dipping interface you want to find out what is the velocity beneath and how much dip this interface is having, and what is the value of the critical angle that you can find using the concept of dipping layer method. And in dipping layer method, what you are going to do, you are going to conduct a reverse profile, which means that if suppose you have a source here and you have a receiver here on the surface, then you can take your measurement and the source will release the energy in the form of wave, and these wave will travel in the downward direction, will hit the interface and will travel along the interface. If it is at the critical angle, then will come back to the receiver. Then in that case you can see that the travel time of this head wave can be calculated and can be used to find out the travel time or the geometry of the interface in terms of its dip angle and also the critical angle, and also various other parameters like intercept angle, apparent velocity can also be deduced. Now if suppose you do not know how the interface is basically directing itself, orienting itself in what direction, then you can not get an idea about like what is the up dip direction and what is the down dip direction. So basically there are two things, one is down dip direction, another is the up dip direction. In the case of down dip direction, you are going to have receiver onto the down dip side. In case of up dip direction, you are going to have the receivers onto the up dip direction side. So in the current geometry, you can see your receiver here is on the down dip side. So this is your down dip direction. If suppose you will replace receiver with the source and source will be replaced by receiver, then in that case your receiver will be on the up dip direction side. That means you are taking the up dip direction. So that is what it is written. Conducting a reverse profile yields the travel times for a ray path in both the down dip and the up dip directions. Since we do not know the orientation of the interface, that means up dip and the down dip direction, we arbitrarily consider one as the forward and other as a reverse direction. So what does it mean is, it means that if suppose at the surface, this is your surface here, and you have your source somewhere here and your receiver is somewhere here, and this is your dipping interface here, and this dipping interface, since you do not know about the orientation of the interface, where in which direction it is having the up dip and in which direction it is the down dip, obviously you won't be knowing because you do not know what is there underneath the surface. That is why you are conducting this survey. So in that case, you cannot identify which one is the up dip direction and which one is the down dip direction. So for that case, what we do, we generally say that we consider one direction as the forward profile and another direction as the reverse profile. So if we are conducting our survey keeping the source somewhere over here and receiver as in this direction, then we can say that this direction is the forward profile and the waves will go like this and will be recorded over here. In the next step, we are going to keep our source in the place of the receiver here. This will be your source and this will be over here is your receiver. And then in that case, what you are going to do, you are going to conduct this survey and then you will be sending some energy and that will be recorded at the receiver. And this case we will say that this is your reverse direction. So when a refractor dips, the slope of the travel time curve does not represent the true layer velocity. So in the horizontal layer case, whatever velocity we were calculating, those were the true layer velocity. But in the case of the dipping layer method, the velocities that you are calculating from the travel time curve, from the slope of the travel time curve, will represent the apparent velocity, not the true velocity. So shooting up dip, that means geophones are on the up dip side of the shot, apparent refractor velocity will be higher. That we are going to see in just a while, that how these velocities higher for the up dip directions. So now let's see and have a look at this diagram. There are two kind of diagram. One is this one and another one is this one. Let's take the case of the first one. So in this case, if the source and the receivers are interchanged on the reverse refraction profile, the travel time will remain unchanged. So basically what it is saying, if your source is here and receiver is here, whatever travel time you are going to calculate will be similar to what if you interchange the position of source and the receivers. So if in the case, if you have a source and your receiver is in up dip direction and another receiver is in the down dip direction, but the distance between the source and the receiver on the surface are same, but their travel time will be different because the head wave is experiencing different dipping interfaces, or you can say the sampling of the head wave will be in the opposite direction and the dipping of the intercept will be differently. So that is what it is written. Different up dip and down dip travel times occur because for a given source position, waves going the same distance along the surface in opposite direction sample the dipping interface differently. Now let's calculate the apparent velocity of the refractor in case of up dip and the down dip directions. And in this geometry, the depth to the interface below the surface and the receiver differ due to the dip angle. So you can see there is this surface and you have a dipping reflector over here, or you can say dipping refractor over here, and your source is located at this position, receiver is located at this position, and the distance between them along the surface is x, and you can see that the source to the refractor perpendicular distance is hd and the receiver to the refracted perpendicular distance is hd plus x sin theta, where theta is the angle of the dip of the refractor and IC is the critical angle, and likewise the velocity of the refractor is V0, or you can say the velocity at the top portion of the refractor is V0 and below the boundary the velocity is V1. Now let's consider the down dip ray path. That means the source is exciting some energy and the waves are traveling in the downward direction towards the interface, and because it is hitting the interface at the critical angle, so it will travel along the interface and then it will be reflected back to the receiver and will be recorded at the receiver. Now we need to calculate the travel time for this head wave in this down dip direction. So that is what it is written, TDX, that means the travel time of the head wave in down dip direction with respect to the offset x is equal to x cos theta minus 2hd plus x sin theta tan IC by V1. That means this is the velocity or this is the travel time along the interface. That means the travel time of this portion of the head wave over here. Now, to calculate the travel time of the downgoing wave and the upgoing wave, we can sum them up, the travel time, and collectively we can write the travel time for both the downgoing directed wave and the upgoing wave. We can write something like this, 2hd plus x sin theta by V naught cos IC. So I am not going into the derivation of this particular portion because it is quite simple and you can just use some trigonometry to calculate these TDX, because you just have to just look at this triangle here to calculate the travel time of this path, and you will have to look at this triangle to calculate the travel time of this particular path, and then you can easily calculate the travel time for the head wave over here. Now, if you will rearrange this particular expression, this will become TDX is equal to x cos theta sin IC by V naught plus 2hd plus x sin theta in bracket 1 minus sin square IC by V naught cos IC. Then finally what you will get x sin IC plus theta by V naught plus 2hd cos IC by V naught is equal to, then you can basically what you do, you can take this down below over here, sin IC plus theta, and then collectively this thing can be called as Vd, that is the apparent velocity in the down dip direction. So the total travel time in down dip direction will be x by Vd plus tau d. Tau d is the intercept time, and then what you can do, you can just take the same thing in the opposite direction. That means you will keep your source over here in the place of the receiver, and the receiver will be located in the place of the source. Now when you do so, your travel time in the up dip direction can be represented by TUX. That will be just similar to what we got in the previous case for the up dip direction, for the down dip direction, and in the up dip direction your equation will become something like this. So here HD that you are seeing here, that's HD is the distance, perpendicular distance from source to the interface. Likewise here you have HU. When you have source over here in this particular position, then this particular thing will be called as HU. Now TUX will be equal to x sin IC minus theta by V naught plus 2HU cos IC by V naught, that will be equal to x by VU plus tau u. So this tau u is the intercept time. Now you can think of like if the tau d and tau u are similar to each other, equal to each other, or different from each other, that we will see in just a while. The apparent velocity in up dip direction and down dip direction can be written like this. So you can look at these expressions. You can easily see that the V naught upon cos sin IC by minus theta will be the apparent velocity in up dip direction. Likewise, for the velocity in the down dip direction, this will be your velocity in down dip direction, V naught by sin IC plus theta. So if you compare these velocities together, then you can easily say that the apparent velocity in up dip direction is greater than the velocity in the down dip direction. That means the apparent velocity in down dip direction are smaller than the velocity in the up dip direction, because this IC plus theta is larger, then overall value will become smaller, and IC minus theta is smaller, then the overall velocity will become larger, which means that VU will be greater than VD. So the intercept times you can calculate from the previous equation. This is your intercept time, and that you can see that for the up dip case the intercept time is 2HU cos IC by V naught, and the intercept time for the down dip case is 2HD cos IC by V naught. So the direct wave travel time is same in both the directions, so the crossover distances differ. So you can see, let's look at this particular diagram. In this case, you can see there are the two travel time curve. One is for the reverse profiling, one is for the forward profiling. If I am calling this is for the forward profiling, then it will be for the reverse profiling. And for the forward profiling, the direct wave is something like this, and then you have the head wave over here, and wherever the direct phase and the head wave are intersecting, that is your crossover distance. This is the crossover distance for the forward case, and here you have this direct phase, and then you have a head wave here, and wherever they are intersecting, if you take a perpendicular onto the x-axis, that will be your crossover distance on the x-axis. This is your xd. In this case, this is your xd. Now the slope of the direct phase will give you the velocity of the top layer. So slope in both of the cases, in the forward profiling and the reverse profiling, will be similar. So the slope are same, you can see these are the same. And if you look at the intercept time of the head wave for the forward profiling, then this is your intercept time here, and in this case this is your intercept time here. So you can easily see both the intercept times are different from each other, and you can think of like one may be bigger than the other. And the travel time plot for a reverse profile and its interpretation, the up dip and the down dip slopes and the intercept differs. So that means you can interpret that the travel time for the head wave in both the directions are different, because you can see the total intercept that you can calculate, this is different than this one total. So basically you can easily say that the total travel time for the head wave in the forward profiling and in the reverse profiling are different from each other. Now the slope of the direct and the head wave travel time yield the dip angle. So you can easily calculate this theta, and also IC, the formula for the dip angle and for the critical angle. So for the dip angle, it is half sine inverse velocity top layer divided by apparent down dip velocity minus sine inverse velocity of the top layer divided by apparent up dip velocity, and then this minus sign will be replaced by plus sign in the case of critical angle. So you can calculate the critical angle. So the half space velocity v1 is found from the critical angle and v0, and the intercept times then yields the layer thicknesses, and by reciprocity the two experiments give the same travel time. Thus for a ray path connecting 2 points, it does not matter whether the wave travels up or down dip. So by contrast, for two receivers at the same distance from a source, one up dip and one down dip, the travel times differ because the ray path encounter the dipping interfaces at different depths. The travel times for two sources at the same distances from a receiver, one up dip and the one down dip, that will also differ. If the dip were 0, then travel times would be same for all the cases, because all they encounter the interface at the same depth. For a flat geometry, the travel time depends only on the distance between the source and the receiver, but in this case it will depend upon the dip also. And the dip found from a reverse profile is not a true dip if the profile is not perpendicular to the strike of the layer. Instead, the measured dip is an apparent dip along the profile. Now we will see how refraction seismology can be helpful in finding the features of the crystal structure. So that application we are going to see now in few of the slides. So you can look at this particular travel time curve, and you can see on the x-axis distances are given in kilometers, on the y-axis the time is given in seconds, and this particular refraction experiment was performed to find out the crystal structure by a scientist named A. Morovicic in 1909. And what he observed when he conducted this refraction data, then he observed that there are the waves which are traveling in the deep high velocity layer with velocity 7.7 kilometer per second, and there was a second wave that he observed which was little slower, and he identified that these are maybe traveling in the upper layer of the crust. So what was those waves? One was PG, another one was PN. He said that PN may be traveling with a higher velocity, that is why it is having the shallower slope. So he identified this layer as this particular wave as the head wave traveling across the boundary between the crust and the mantle, and PG he identified as the wave that is traveling in the crust with little lower velocity of 5.6 km per second. Using his data, he also found out the thickness of the crust, which was about 50 km, and then he identified the boundary, that means along which the PN wave was traveling between those two layers, and he identified that layer as Morovicic discontinuity. This is the discontinuity which separates crust from the mantle, and then he said that the PN is basically a head wave and the PG is basically the direct phase, and then he also said that the G term that he gave for the nomenclature of PG is basically representing the granite, that means it is traveling in the granitic structure of the crust. Similarly, he saw the waves for the S wave, that is SG and SN here, and those were also having, one was traveling as the head wave, one was basically traveling as the direct phase. And this particular experiment was basically responsible to identify the Morovicic discontinuity. And Morovicic discontinuity is a very important part in understanding the crustal structure all across the globe. Now, the things come, what are PN velocities? So PN velocity is a seismic phase that travels at the crust mantle interface. The apparent velocity of PN gives an average of mantle velocity along the path that it traveled. So let's suppose this is your surface and there you have a crust, and then there is an interface below which you have a mantle. Right. So the PN wave basically travels at this particular interface, that means in between crust and mantle along the boundary, and then this, when it travels along this boundary, these P wave will be known as PN waves, or you can say the P head wave, and these P head waves are generally observed in the when the source is at a distance of 2 degree and 16 degree, that means the source should be away from the receiver at a distance of 2 degree or maybe less than 16 degree. So when the PN velocities are slow, then you can conclude that the upper mantle may be made up of warm material. When PN velocities are fast, you may say that the upper mantle may be made up of the material that is having the lower temperature. This is the reduced travel time plot, or you can say it is a record section, which means that the seismogram associated with an earthquake has been recorded at various distances along the surface, and all those seismograms are put up together, being the x-axis representing the distance in epicentral in kilometers, and y-axis is basically having the reduced travel time, that means time minus x by 6. So basically 6 is the factor that is taken for a specific velocity to reduce the velocity of the travel time curve, so that we can easily distinguish between different kind of velocities such as PG velocities and the PN velocities. If you look at this particular diagram, then you can see that there is a particular move out that you can observe along the PG. So you can see this is the move out, and this move out is basically having the positive slope. That means the velocities of less than 6 km per second, that may be because the PG waves generally travels in the crust, and there is a move out for the PN waves also here, and that is having the negative slope, that may be because the velocity is greater than 6 for this particular wave where it is traveling, that is maybe it is traveling in the mantle. So basically you can say that the reduced travel time plot provides an easy way to distinguish between velocities. Now look at this another example for the identification of various features of the crust. So this is the particular model, that is, you can say, synthetic model, and in which the crust has been divided into several layers, which means we are talking about the oceanic crust here. So first you have the water column, then you have the sediments, and then you have the crustal rocks. And between crustal rocks and the mantle, there is a discontinuity, that is the Moho discontinuity. So basically, what is happening when you create the synthetic seismograms from various receivers located at various distances from the source, then you can get this kind of picture. These kind of synthetic seismograms in the reduced travel time plot. Here the reduced travel velocity has been taken as 8 km per second. In the synthetic seismogram, for this model, P2, P3, Pn are the head waves from the layer 2 and 3 and the mantle. So this is your layer number 2. Let me rub it up. So this is your layer number 2, this is layer number 3, and here you have mantle. So that this is what it is saying. P2, P3 and Pn are the head waves from layer 2, 3 and the mantle. P3P and PMP are the reflection of the top of the layer 3 and the mantle. So this is the synthetic seismogram plot. Now see the real seismogram plot, that means the data from the real source. Then what you can observe is that the multiples associated with P3P are absent in the real data, which signifies that the transition between layer 2 and layer 3 is not sharp. It is basically having the gradient nature. So in this particular diagram, this basically represents that into the oceans, the transitions between the sediment and the crustal layers are not basically a sharp transition. It is basically a gradient between both of the layers. That is why the P3P multiple is absent in this particular case. Now we can say, after having the review of the examples that we just discussed, that the velocity structure can be often interpreted in terms of composition also. If we have velocity variations, density variations, elastic properties variations, we can generally correlate those variations with the specific type of mineral composition, and then also can be identify the chemical compositions of the material with which those velocities and the density variations are occurring in the rocks. For this purpose, not only seismology is sufficient, you can also integrate various other techniques in order to find out the detailed view of the velocities in the rock. So for that purpose, you can also take help of the other geophysical techniques such as the gravity methods, magnetotelluric method. You can also conduct the geophysical fieldwork and the laboratory studies to basically infer the seismic velocities of the rocks. Also, you can interpret the seismological result for the crust and the mantle in terms of composition requires knowing something about the rocks and the minerals that compose them. Also, the properties that the rocks have, such as the density variations and the seismic velocity variations, those can be helpful to identify the mineral compositions of the rocks. So these are the references, and in the next class we are going to talk about reflection seismology, and that is all for today. Thank you so much. Bye bye.